but I'm going to talk about urban science this afternoon. And in particular, I'm going to talk about complexity and scaling. There are obviously many aspects of urban science that we could talk about. There are indeed many urban sciences. If we were to define urban science, then you would find there are a lot of different definitions, dependent on different perspectives. But I'll mainly be talking about an urban science that really relates to thinking about cities as physical systems, in analogy to some extent with statistical physics, in a way. Many of the ideas are drawn from statistical physics. This is not an urban science that we're talking about how we construct cities in terms of building or anything like that. It'll be looking at the phenomenology, really, of urban science. Okay, so I've explained to you I'll talk about urban science, and let me tell you a little bit about what I'm going to talk about this afternoon in terms of the topics. I'm going to begin by talking a bit about complexity theory and introduce to you, if you don't know it already, the systems approach, which really is related to thinking about how systems are organized from the top down, as it were, highly centralized systems. I'll talk a little bit about temporal dynamics, and that'll lead me on to talking about complex systems, which is thinking about how systems are organized from the bottom up in that sense. The idea of top down, the systems approach, to bottom up, the complexity approach, is quite key to the evolution of ideas in this particular field. That we began with the systems approach. We thought of cities as being organized from the top down, a bit like machines in a sense. And over the last 50 years, the science has evolved to deal with complex systems that really are more like biological organisms than they are like machines in that sense. So it's a switch really from mechanics to some extent to biology in that sense. And complexity theory really treats, in our case, cities as being systems which are organized from the bottom up. And in that sense, it gives them a degree of unpredictability that is not characteristic of systems ordered from the top down. So I'll talk about complexity theory, and then I'll begin to talk about size and scale and look at the fundamental relationships between size and scale. This really will introduce ideas about power laws, the idea that things scale according to various powers, in a sense, as they grow and change in this particular context. And also, I'll look at how those really relate to different types of cities, basically, which are predominantly due to the different sizes. And then I'll talk about complexity as entropy. I'll spend really probably about a third of the talk, the last third of the talk, talking about complexity and entropy. I'll talk about entropy maximizing, how we can define entropy as a tool to look at order in systems or disorder, and then talk about how we derive models that maximize entropy that are subject to constraint. It's a sort of standard tool which is used in statistical physics. And then I'll talk a little bit about substantive insights, entropy as variety, spread, and complexity. I'll then talk about some, if we have time, basically, defining entropy using probabilities, and then moving on to entropy thinking in terms of the density model. And last but not least, ideas about shape, distribution, and spatial entropy as complexity in that sense. Now, there's quite a lot of material here. I'll probably go on for about 50 minutes or so. That gives you an idea. If there's any problem about limiting the amount of time, then please tell me as we go along. Okay, so what is complexity? Now, the earliest and best statements of complexity really go back at least 50 years. They probably go back 70 or 80 years to immediately after World War II, basically. Warren Weaver, who wrote a short book with Claude Shannon on information theory, basically in the late 40s. In that sense, Warren Weaver, who was the director of the Rockefeller Foundation in New York, in his valedictory address, that means that in his leaving address, basically, he talked about the idea of science and complexity. And he said, really, there are three different approaches to science, in a sense, that have evolved over the last 200 years or so, since the Industrial Revolution. Well, I suppose since the Enlightenment, since Newton and Leibniz and so on. And he said the first approach was based on thinking about systems as problems of simplicity, simple systems. And physics prior to about 1900 was largely dealing with relatively simple systems, etc., such as the rotation of the planets, as it were, in the solar system, the movement of mass at that particular scale. These were problems of simplicity. And then really with the emergence of quantum theory and the splitting of the atom and so on, physics began to move to problems of disorganized complexity. To some extent, statistical physics really depends on disorganized complexity in some sense. The statistical elements of physics in this context of very large numbers of atoms, for example, or molecules, really relates to this idea of order or disorder in a system. And that was really the second approach. And the third approach, which he said was the emergent approach, this was in the middle of the last century, was thinking about systems as problems of organized complexity. And these were biological and human systems in particular, those that we're interested in here, cities and societies. And this was really the shift to thinking about how systems got organized, really from the bottom up. And it was this shift really from the mechanical world of problems of complexity, etc., all the way through to the biological world, where we began to think about the essence of our cities as being more like biological entities, organisms, as it were, living beings in some sense, or living systems in this context, in contrast from machine systems, which really was the earlier approach. So complexity theory is really all about thinking about how systems evolve, really, grow and evolve and develop, really, from the bottom up in this particular context. Let me throw some ideas onto the table here where you can get some information about this. There's a great paper by Warren Weaver. This is valedictory address, Science and Complexity, in a sense. And if you want a version of that in the cities area, then the book by Jane Jacobs, published in 1961, called The Death and Life of Great American Cities, which is a wonderful book about planning and the problems of planning. But in the last chapter, she talks about how we should address problems of order and disorder in cities. And she really alludes to Warren Weaver's Science and Complexity paper. There's a number of other papers that are worth having a look at. Herbert Simon, a Nobel Prize winner in psychology, I think, and computer science, and perhaps economics too. But Herbert Simon wrote a paper in about 1960, 61 or so, called The Architecture of Complexity. And that's an excellent paper thinking about the structure of complex systems, in a sense. And last but not least, there's a short monograph edited by Michael Mahaffey, which is a commentary by a large number of us, myself included, on Christopher Alexander's famous paper, The City is Not a Tree. And this is really saying that the city is much more complicated than a tree system. It's more like a forest, in a sense, where you have lots of overlapping relationships and so on. So these are four different elements of the literature that give you a very good idea of complexity theory. Okay, so let's move on. Now, there are no really watertight definitions of what complexity theory is. First of all, there's the notion that no longer in science, in complexity theory, that is there any acceptance of the fact that there are watertight theories that lead to firm and definite predictions. One of the consequences of complexity theory is that we tend to now think of the world as being intrinsically unpredictable. I read a title of an article on the pandemic in The Economist the other week, which was actually called Predictable Unpredictability, saying that the unpredictable world was the only thing that we could ever predict, in a sense, that things coming out of the blue were really the consequence of the world we live in that sense. And to some extent, this is a relaxation of the modern canons of science, really, dealing with the fact that science no longer is in the business of enabling us to make firm predictions. It probably never was, or it only ever was in very simple systems, in closed systems, in a sense, where we closed them from all other exogenous influences. So, for example, the theory of hydrodynamics is a closed system, and that tells you how matter and air and so on really relate to one another, in a sense, gives you some equations for dealing with that. But as soon as you begin to use them in things like weather forecasting and so on, then you're opening the system to lots of different extraneous events, which we can't really deal with in that particular context. And the system is no longer closed. So to some extent, complexity theory more or less says that the old idea that the system is closed, that we can close it from the rest of the world and study it, etc., is really very much a figment of our imaginations. The world really isn't like that, and we'll never be able to explain anything if we kind of hold to the view that we can separate our system of interest from the wider environmental context. We may have to do that so that we can simply proceed. Okay, so inherent unpredictability is the essence of complex systems. The second idea is that in a complex system, as indeed in any system, whether it be a machine system or a biological system, top-down or bottom-up, there are explicit interactions between many and multiple elements. And this really defines, to some extent, the scale. So if, for example, there are P elements, capital P elements, then simply by defining interactions between each of these elements, we get, for example, P squared connections. So if you think of P as being the size of the city, let's assume that we're talking about Rome in the first century AD, basically, in that sense, which Rome had about 1 million people then, basically, then the number of potential interactions in Rome was P squared, which is 1 million times 1 million, basically, in that sense, sort of billion. In this particular context, if we think of a city half the size, then we're talking about an order of magnitude difference. If we think of a city of 500,000, then 500,000 times 500,000 squared is a much smaller number of interactions pro rata than the million times the million. So in other words, as the city gets bigger, the number of interactions increases exponentially. It increases in this context to the square of the size in this sense. And this raises the whole notion of interactions, connections, networks and so on as being really central to complexity theory. So that's our second notion, the idea of interactions. Now, the third notion, in fact, is really what I've just said, basically as part of the second, in a sense that as the world becomes more complex, that P, the size of the objects get bigger and the number of interactions begin to grow exponentially. Of course, we can't really define the possible number of interactions as a measure of complexity as such. Life is much more complex than this, but it does give some sense of how absolute complexity can be approached. It gives us a handle, if you like, on the complexity of the system, the size and the interactions, etc. Now, the other feature, of course, the fourth notion is that these interactions are changing all the time. Not only do we have one type of interaction in a city between people. If, for example, you think of people in a city and the friends of people in that sense, the friends of ourselves in this sense, that gives us some idea of the number of interactions, basically, that if there were P people in the city, if there were 1 million people in the city, and 1 million squared potential interactions, we clearly couldn't have each of us couldn't have 1 million friends. It's far too much. It's much more likely we're going to have something in the order of about 250 friends, basically. In that sense, this is Dunbar's number, basically. Robin Dunbar from Oxford basically worked out that the typical number of friends that you actually have in a place is something in the order of about 200 to 300 in this sense. So in other words, rather than 1 million times 1 million, we're talking about each of those 1 million people in the city has about 250 friends. So it's a lot less than the actual p squared. So there are qualitative changes with respect to the types of interactions, basically, in that sense. We can have lots and lots of interactions, friends, for example, social friends. We can have journey to work interactions, work colleagues, and so on. There are countless interactions that we can actually have with one another in the city. And this, of course, when we add all of these things together and plot them out as networks, really does begin to define the idea that the city is a complex system. Okay, let me move on to the systems approach and say something about that. Order from the top down, basically. By and large, in the 19th century, people thought of society and cities as being organized more like machines. The machine analogy was the sort of central issue in terms of thinking about cities in the 19th cities and society in the 19th centuries. And in some senses, as soon as we begin to think about the development of cities in the 19th century, then we're thinking about how to make them more ordered. And planning, urban planning, is all about introducing order into systems that were seen to some extent as really chaotic in this particular context. There are lots of ideas about cities in terms of the newer approach, complexity theory, in terms of chaos, and I'll mention some of these in a moment in this particular context. So onto the agenda in the 1960s came this idea that cities really were organized from the top down. They were well-ordered systems, and when we looked at them, they looked well-ordered. They had well-defined central business districts, the core or the town centre, the city centre. They had radial rings of different land use dependent on the economic profitability. So a good deal of urban economics is based on this notion of the system being in equilibrium, where the different rings of land use and activities around the centre basically are defined by the way the market works in some sense. And this was really the form and the physical morphology of the city that led to this notion that really we could explain it using ideas from the top down in this particular context. And as I said, that lots of models of cities were built on the assumption that we could actually model them in this particular way from the top down, in a sense. All of this really led to lots of ideas about the development of dynamics in cities. So, for example, ideas about systems theory and cybernetics really came from people like Norbert Wiener. He defined cybernetics as the control and communication in the animal and machine, basically. And this led to the idea of general systems theory. Lots of these ideas still accepted the notion that cities could be organized really from the top down, but there were lots of ideas relating to networks and interactions and chaos and things of that sort that began to creep into systems theory. And this effectively changed systems theory. It changed it to people beginning to think, well, maybe this top-down model to explain things is not really the most appropriate model, because urban planning assumes that to some extent we're intervening in systems really from the top down in this particular context. Okay, lots of ideas in terms of systems theory came onto the agenda. The idea that, for example, systems could be organized as sets of subsystems. You can see this little diagram here with people at different levels, either the individual or the group, or the system itself. And you can also see on the right-hand side the idea of a hierarchy in some sense of systems. So hierarchy and subsystems, dividing a system into its subsystems. So for example, we could divide a city into a retail system, a residential system, an industrial system, and so on. And we could think of those as being arranged hierarchically in the system. If you look at, for example, retailing, shopping in the system, then normally there's one large town centre with certain specialist retail functions, and then a series of sub-centres and sub-sub-centres all the way down to neighbourhood centres and neighbourhood shops. You see a distinct hierarchy of organisation, and that is the same in terms of the road system, the retail system, the road system, the educational system. These are all hierarchical systems. You normally only have one, or not many more than one anyway, university in a place, but you have many different schools. And this is the notion of, hierarchy in the educational system, which is replicated in terms of the way cities look like. Now, here's the classic example of hierarchy, and this is taken from a book by a chap called Walter Kristalla. The picture on the left-hand side is the hinterlands, or areas around towns in southern Germany. This was a book written in 1933 called Central Place Theory in Southern Germany. These were called central places. And the idea is that clearly when you look at the number of places, you have a small number of very big centres with big hinterlands and a very large number of small centres with little hinterlands, etc. And they're nested in this way. And the reason why all this occurs is because of the way the economy works, why the spatial economy. This is on the left-hand side, you see sizes in terms of what goes on between cities. So this is a landscape in southern Germany over a matter of hundreds of kilometers, say, whereas the right-hand side is what goes on inside the city. And you can see these zones of concentric land use. This is von Thunen's model. I should say that the German developments in Germany in the 19th century and early 20th century really led to this area which is called location theory. And location theory is all about applying economic concepts to the organization of things in space. Okay, here's an example which is a little bit more focused in terms of what we see in urban design inside of cities. This is from Alexander's famous paper, The City is Not a Tree, where you see you have overlapping subsystems, and we have a tree-like system for Chandigarh, which is the ideal town in the idealized city in Pakistan. And then you've also got Manhattan, which is much more diverse, basically. Now, I'm not going to go into this, but a lot of diversity in cities really pertains to the way hierarchies function in this particular context. Now, I'm going to miss this bit on temporal dynamics. It's a little bit about catastrophes and bifurcations and chaos and so on, in a sense, but I'm going to miss it largely because we've got a lot of material here, and I want to move on to thinking specifically about complex systems, and then actually giving you some examples really in this particular context. So let's have a look at some of these ideas. One of the kind of key features of a city as a complex system is that when we look at how it emerges, the patterns in a city tend to emerge by actions really from the bottom up. So the decisions you make about where you live, in a sense, and where you shop, and what kind of transport you use and so on, are all done from an individual point of view. You're not particularly coordinating with everybody else in the city. But out of this apparently uncoordinated action come emergent patterns of order. Now, let's have a look at some of these. This is where we begin to get into some examples, basically. The picture on the top left is the reddy, orangey blobs, basically, in a sense, is population density in Greater London, in the London region. That area is probably about 100 kilometres across, maybe 120 or 30 kilometres across, and about 90 or 100 kilometres north-south, in a sense. And you can see that what is very clear is that nobody planned it, basically. This is not something that is organised from the top down. It grows from the bottom up. And as these settlements and villages that comprise Greater London change in size over time as they grow, basically, then we get more and more clusters of activity in this particular context. So the yellow through red represents the density, and as you'd expect, the density is higher in the center because people would like to get to the center, and it's more prosperous in that sense, and therefore more and more people crowd in. So the densities increase in this particular context. And one of the other features is that this really looks like the growth of something like a biological system, like a tumor in some sense. I mean, not necessarily an infectious tumor, but a benign tumor in some sense. But anyway, a growth system in this particular context. And when we look at cities everywhere, then we begin to see these clusters which look statistically fairly similar in this particular context. So if we look at the top right-hand picture, this is actually scaling up. London sits in the bottom right-hand corner of the top right-hand graph, basically, and Birmingham, you can see. And when we go on to the second line, we see the blobs basically in the UK. You can just about make out the blobs of the big cities in the UK. And then there's a picture of Europe, Nightlight's photograph from Europe and so on. And you can sort of see that contained in all of this is the notion that these systems are growing from the bottom up. You can also see that there are very few really big clusters and lots of little clusters. We're really saying very few big towns and lots of small towns in that sense. Now, that's very important because the essence of looking at the distribution of towns over size is really a very central issue in terms of scaling and the statistical organization of this. If we look at the bottom line, again, we've got Britain, and then we've got Europe, and we've also got Greater London again. And this is looking at retail centres, in fact, in Greater London. So another hierarchy. And you can also see another feature of this, that the radial structure, the structure of roads coming into these big places, is also determining the morphology in that sense. And on the immediate right-hand side, we see one of the Palm Islands in the United Arab Emirates, which is actually, it's in Dubai, basically. And you can see the idea of how, for example, development is spreading in this hostile medium. These Palm Islands are basically built in the sea, basically, where you can see that that's a hostile medium for urban development in a sense, and they grow out according to where people want to actually locate in terms of space, basically. So in that context, the development is highly constrained in terms of cost. Now, you can see in all of this that we're talking about clusters that spread in some sense. We're talking about spread. So lots of ideas in physics begin to make sense in terms of these pictures: diffusion, hierarchy, spread, emergence from the bottom up, patterns that emerge by developing from the bottom up in this sense. All of these ideas, and of course even networks, for example, the picture of the retailing on the bottom line, basically the second to right on the bottom line of London and shopping, basically really introduced this idea of networks. So in all of these things we're talking about, these are really the signatures of a complex system in that sense. So let me make a few key points about complexity, and then we'll begin to look more formally at some of these ideas pertaining to statistical physics and so on, which probably is more interesting to you to some extent in terms of the development of your course in the way. Okay, so 4 key points. The patterns emerge as order from the product of multiple non-coordinated decisions. That does not mean that these are random decisions. It's just that they're not coordinated in any way. When I make a trip on a train or a bus, for example, somebody else traveling on the same is not coordinating their decision with me in some sense. So a good deal, in fact, most of what goes on in cities is non-coordinated at this level. Now, some order is established at intermediate scales. So it's not as though everything works from the bottom up. That would, to some extent, mean there was no structure whatsoever to society. There are various groups of people operating at different levels. So to some extent, we really have to loosen this notion of the complex system as being an emergent structure from the bottom up. It's also a product of some things that happen top down. So it's a combination of bottom up and top down. Now, the ultimate structure is the product of historical accidents, frozen accidents, or path dependence, as it's called. History matters with respect to the final form we end up with in this particular context. So, in other words, history is all important. A random choice at some particular point, some expected change, really makes a difference, in a sense, in terms of the final thing we end up with. And the patterns that emerge are often self-similar. They repeat themselves at different scales. And patterns that repeat themselves at different scales are called fractals, basically. Fractal geometry is all about a pattern that repeats itself. And if you look at the little pictures here, something like Sierpinski sort of form, etc., you can actually see that as we kind of drill down in terms of magnification, we see the same structure appearing at different finer scales. So as our scale changes, the picture is revealed. There is this stability or self-similarity, sometimes called self-affinity in a slightly looser version, self-similarity with respect to the patterns themselves. Now, let me just go back to these pictures here. Then you can begin to see that some of the little clusters are statistically self-similar to the big cluster of London in this particular context. And in that sense, these patterns too are fractal, basically. Everywhere we look in terms of spatial variation, how things spread out in space really reveal fractal clusters, hierarchical clusters, structure on all levels in that sense. Now, all of these ideas about scale really relate to the signatures of a complex system. And in a sense, if we're able to measure the scale of these things in cities, then we can say something about their relative complexity and indeed how they change over time. So let's have a look at these ideas about size and scale. Let's look at the fundamental relations. Now, I'm going to stop at that point and look how I'm doing. Okay, I'm on about 2:30 by my time, probably 3:30 by your time. So I'll be going for another about half hour or so, probably maybe a little bit less in that sense. So let's talk about size and scale, the fundamental relations. Now we can define three kinds of scaling that at least three kinds of scaling that we can develop with respect to the generic size of a system. And we'll take the generic size of a system as being the variable P, which is the population in that sense. And we've already seen that if we look at the number of interactions between a population P, then an obviously simple set of interactions is to assume that every individual in the population P interacts with every other individual, and that leads to the power P, basically, in that sense. So P squared is the number of interactions. So we could say there are two elements of size here. One is P, which is the absolute size in that sense. The other is P squared, which is the number of interactions. Well, of course, we could have the population raised to a power different from 2 in that sense. So if the power were greater than 1 in that sense, but it wasn't in any sense 2, then we call this positive allometry, basically. The relationship between the size of an object and the number of interactions that it generates is referred to fairly casually, I think, in biology as allometry. In that sense, a positive allometry is where the power of the object, which is under consideration, population in this sense, is greater than 1 in this particular context. And the greater the power more than one, the more than proportionate the growth in interactions as the population actually changes. Now, if it is less than one, this is negative allometry, basically. So in other words, if P, instead of being squared or instead of being 1.5, if P were raised to the power 0.5, which is the square root of P, basically, then the number of interactions would get less as the number of population got greater in that sense. And that would be negative allometry in a sense. So now, in fact, there's a very obvious comparison between the idea of positive allometry and negative allometry in what the economists call agglomeration economies, where you get economies of scale. Basically, they call it economies of scale too, where you get positive economies of scale or agglomeration economies. This means that as things get bigger, the things that spin off from them, such as wealth and income, get more than proportionately bigger. So if I'm in a city of 1 million people, this might give me P, let's say P raised to the power 1.1 is the amount of wealth or wages. But if P is 2 million people, then the power of the scale, basically, the positive allometry, would give me more than proportionately greater than P to the 1.1 in this particular context. So, in other words, as the scale increases in this context, then the spin-offs from the scale, basically, the more than proportionate increases begin to increase as the scale changes in that sense. And so if we're interested in the wealth of a system, then we often find that there's a relationship such as wealth is proportional to, let's say, population raised to the power A or alpha, where alpha, in fact, is greater than 1. If it was 1, then the wealth would be the same as the population in that sense. If it's 1.1, then you can actually see that the wealth is proportionately greater, not massively greater with 1.1, quite dramatically greater if A was equal to 2 in that sense. So, and this relationship between income or wealth and the system, and it could be lots of other variables too. It doesn't have to be wealth. It could be any variable that really relates to the interactions between population or objects in a system. Then the obvious issue in this particular context is raising P to greater than 1 in that sense, giving rise to increasing income. The implication being that if you live in a bigger city, then all other things being equal, your wealth or your wages will be greater than if you live in a little city, basically, in that sense. So if you live in Rome, you're more likely to get, on average, for the same job, more income than if you were to live in, I don't know, Verona or Venice or something like that, basically. I don't know, but if I change it to the British example, then the wages are manifestly much greater in London than they are in, say, Manchester or Liverpool or any of the towns which are much smaller in that sense. Okay, and of course, this relationship, this allometric relationship between size and income or wealth, basically in this sense, the economies of scale, has been quite widely exploited in a number of articles by Louis Betancourt and his colleagues, and also contained in a book by Jeff West called Scale, basically, where he looks at positive allometry, not just in cities, basically, that's one of his examples, but he looks at it in terms of, firms, the economy. He looks at it in terms of lots of ideas about fractals in biological systems as well, in that sense. Okay, so our first scaling relation is allometry. This is where we get where population is raised to, or the object in question is raised to a power greater than or less than 1, basically, in that sense, positive and negative allometry. Now, the second relation is sort of derived from this, and at this point, it really relates back to the attenuation of the effect of interconnections in this particular way, with some element of distance, basically. And this introduces the idea of the gravitational model. We'll come back to that, really. So the equation there shows you that the amount of interaction is equal to, between any two populations, is equal to the population multiplied by itself, which is the total number of interactions, but divided by some kind of measure, which is an inhibiting effect, basically. In other words, if I have 1 million people and I can't possibly have 1 million squared interactions, there can't be 1 million squared friendships in a city of 1 million people, basically. In that sense, there has to be some attenuation with respect to the space. And of course, in a city of, let's say, in a city of 100 people, then, you know, they're much closer together at a certain density than in a city of 1 million people, in that sense. So there is a measure of D which really relates to size. And to some extent, this is really a kind of roundabout way of generating the gravity model, that the scaling relations with respect to size tend to be the mass equations in a gravity model, and the inhibiting effects are this distance, for example, in this particular case, are the inhibiting effects, the deterrent effects. So really the amount of interactions are balanced between the scaling relations and these deterrent effects, these economies of agglomeration, if you like, on the top line, and the diseconomies, which really relate to a scale on the bottom line. And I make the point here that this is where we can begin to see what Dunbar's number really begins to mean, which is the average number of acquaintances. Okay, so let's actually move on to formalize this as our second scaling relationship, which is the conventional spatial interaction model. Although we've derived it from allometry to some extent, we can actually begin to think of it as a scaling relationship that stands on its own. And this is the conventional gravitational model. So if you look back at Newton's laws of motion, basically, you can find that one of them relates to the force between two objects, basically, which is multiplied by the mass of the two objects. In this case, the mass of the objects is pi and pj, and the deterrent effect between the objects, the thing that lowers the force, is the actual distance. And of course, in Newton's law of motion, he basically says that the force between I and j is equal to some sort of constant, the gravitational constant, we'll call that k, multiplied the mass of I and the mass of j, which might be planets, for example, or in a sense, so the mass of I and the mass of j divided by the square of the distance between I and j. We've actually written here that it's the alpha power of dij, and that is often between 1 and 2 in that sense. So that's our second scaling relationship. First one, allometry. Second one, gravitation or spatial interaction in that particular context, related to one. Now, the third relation is rather different, the third scaling relation in cities, and this relates to the frequency of sizes. If I take a very large number of cities of different sizes and measure their frequency, etc., in other words, that we might have one very big city, two cities which are next in level, in rank, and then 3 cities which are the next down the train. So we start off with, Rome with 1 million people. We then look at our next couple of cities which are 500,000. The next cities down might be sort of 300,000, something of that sort. We might have 3 or 4 of them. So we have a frequency distribution which says that we have a large number of small cities and we have a small number of big cities. Now, there is a rationale that says that to be a big city, you have to be a little city first. And it's sort of fairly obvious that in a growing system from the bottom up, you can only be a little city to begin with, and then you can grow into a big city. But all the cities can't grow into, they can't all be big cities in that sense, for the simple reason that there isn't enough resources. We don't have enough income and wealth and so on to spread around so that everyone can be a big city in that sense. So we can measure the frequency of city size, and it so happens that the frequency of city size is inversely proportional to the size of the city. Now that sounds tautological. Indeed, it is tautological to some extent, but it's an observed fact that, in other words, when we look at the number of cities, the number of cities is inversely proportional to the size of cities. And if we look at the rank of the city relative to its size, this is often called the rank size rule or the rank size law. It follows a power law. So here you can see we have another power law. Let me just go back to, here where we talked about allometry, and then we talked about gravitation. And gravitation here, and now we're talking about frequency. All of these things are power laws. You can see that 1 over some variable to a power, basically, or the variable to the power itself, as in positive allometry. These are laws that basically really relate to scaling. And the scale of, in fact, I think I have something in the next slide or so that tells you why we call it scaling, basically, in that sense. Yes, indeed, it is the last slide. So our third scaling relationship is the rank size rule. It's this particular one that I've just looked at on the bottom of the screen there. The frequency is inversely proportional to some power of the size in that sense. Now, I'm not going to go into this in any detail, but that a lot of the ideas about hierarchies and sizes and frequencies and so on can all be tied together, basically, in that sense. And we call it a scaling law because if you look at the middle lines of this slide, then we say, let's say W equals, which is wealth, is proportional to the population raised to the power of 1.1, or raised to the power of A, basically, in that sense. Now, if we scale population by some scaling constant, which is, let's say, Z or Z, in that sense, then we get the same relation in that sense. And this indicates that it is effectively scaling. It's the same thing, but scaled up by a change in size. So if we look at the equation on this slide, we have the new distribution of wealth is equal to a scaling factor. It might be 2 or 3 or something like that, multiplied by P, raised to the power 1.1, because we scaled the population, but we're raising it to the same power. What happens in that particular context is that the Z factors through in this sense, and the P is to 1.2, and we see basically that the wealth, the new wealth that we get, is still proportional to the old wealth in that sense. It's raised to a different scaling constant in this sense, but the scale effectively is the same. So we're not really changing the wealth qualitatively in any sense. In a way, and that sort of scaling relationship is writ large across the whole idea of scaling, fractals, agglomeration economies, and so on in that sense. Okay, let me check again for time. Okay, so perhaps another 10 or 15 minutes and then we'll be through. Okay, so far we've talked about scaling, we've talked a little bit about statistical ideas, we talked about hierarchies and so on. The other idea that's very central to urban science, and indeed very central to the whole of physics, really, in that sense, certainly statistical physics, is the idea of entropy, basically. And let me introduce two types of entropy in this particular context. First of all, the idea of defining entropy without saying what it is, but using it to generate models which maximize entropy, to cut a long story short, many systems in physics are in equilibrium when entropy is maximized in some sense. And a lot of that relates to the constraints that pertain to the organization of the system, etc. We'll find the same in terms of cities. We can identify some constraints which enable us to identify what people can and cannot do in cities. And we also think about the degree of disorder in the city. We want to actually build a model that really relates to how a city works. So we need certain constraints on the model, which we observe are certainly relevant to a feasible city. And at the same time, we want to give people as much choice as possible, randomness of choice. Then one of the ways of doing this is to define an entropy and maximize it with respect to the constraints. So, and to do this, we really need to, first of all, define a probability. So in terms of our population, what we've got here is our population in location 1 or location I or zone I in that sense, which is the population we could divide by total population, etc. And that gives us a probability, pi, in that sense. So here's our probability, etc. Now the population sums to p, basically, in that sense. So that means that the probabilities will sum to 1. If we define little pi as big pi divided by p, basically, in that sense, then that gives us the probability that's on the previous slide. And when we add those probabilities, they add to 1, basically. Now, in information theory or entropy, basically, we say that the raw information in a probability distribution or an element of a probability distribution is 1 divided by pi. And this is, as you can see, as the probability gets smaller in that third equation down, basically 1 over pi, as the probability gets smaller, the amount of information gets bigger. Now, what does this mean? It means basically that if you have an event that is very improbable, there's a very low probability of the event happening, then the amount of information you get from the event happening is very large. So in other words, if the probability of something happening is infinitesimal in that sense, then the information you get if the event occurs is extremely large. If the probability is almost certain, basically, and if it occurs, you don't really get much information from that. So information is defined really as the sum of the raw informations. And as we'll see in a moment, the sum of the raw informations for a set of events is equal to the entropy. Okay, we can also say that if one event occurs and then another event occurs, which is independent of the first one, then the joint information is given as 1 over p multiplied by pj multiplied by 1 over pi in that context. The information gained, in fact, should not be multiplicative, but it should be additive. In other words, we should be able to add the first information, 1 over pi, to the second information, plus 1 over pj, and that gives us the amount of information, rather than multiplying the events together as though they're independent. So in other words, you can see that what we don't want is 1 over pi pj, which is the two dependent events. We want the information to be separate and additive in this sense. The only function that will allow this is the log of 1 over pi. So the only function that allows us to add these informations together is log over 1 over pi. So we could say really that the raw information is log over 1 over pi. When we add all of these together for lots of pi's, then basically, and we do it for 2 pi's there, as you can see on the in the equation with the big bracket, basically. Then if we add all of the events together, we actually get the entropy. H equals summation over pi log pj. log pi in that sense. Now that's the entropy. The minimum value of the entropy is 0. If you have one probability is 0 and all the other probabilities, one probability of 1, so the one event is certain to happen, and all the other events have a probability of 0, etc., then the total entropy is equal 0, basically. So log of 1 is 0, basically, in that sense. If we have the probabilities all being equal, they're all more likely to occur, then the maximum entropy that we actually get, the greatest degree of choice really in this sense, is equal to log n. So h equals log n when pi equals 1 over n. Now there's lots of things we can do to manipulate these quantities in various ways and to show, and I don't have time this afternoon to be able to do this. This is just giving you a taste of what goes on in this particular world in that sense. Okay, I'm going to skip that. That's basically the entropy relating to two events, basically. So now a lot of this work goes back a long time, basically. I mean, I wrote some papers back in 72, 73, basically. It's not quite 50 years ago, but it is really almost 50 years ago now. Say 45. I must have given this lecture about 3 or 4 years ago, basically, but it is almost 50 years ago since the entropy and spatial geometry paper appeared in Area back in 72, and my spatial entropy paper appeared in Geographical Analysis in 1974. So, I never realized I'd be talking about it again sort of nearly 50 years later. But nevertheless, I mean, that's probably good. Okay, interpreting entropy. Now, what we've looked at so far is what the entropy formula is, basically, in a sense. And there are some things we really need to say, that as the number of events increases, then the entropy increases. So, in other words, a city of 1 million people has an entropy which is much greater than a city of 500,000 people, measuring it using the probabilities of people living in different parts of the city, basically pi. We can also say that the distribution of these events also changes, basically. The shape of the frequency distribution of probabilities also changes in that sense. So in other words, we can think of if this is our city, okay, on the size of the probability on the vertical axis, and the number of partitions of the city, the number of zones of the city on the horizontal axis. In other words, if we just have everybody living in the city center, which is this one here, in that sense, then the probability equals 1, and the maximum entropy equals 0. If everybody lives if everybody is equally distributed along the line, basically, we've already said this, that the probability or the entropy is equal to log over n. So log over n really relates to a uniform distribution, whereas where pi equals 1, basically, and h equals 0, etc., we're talking about an extreme distribution. In that sense, really just a spike in the probability distribution. So you can actually think that between these events, we may have lots of different shapes. So in other words, what we're saying here is that if we think of the city divided into these different units on the horizontal and the size of the probability on the vertical axis, then we can look at lots of different things in between. And it's probably best to think of this as a one-dimensional city, where we've got the bar there, basically, then that's really the city center. And the next one is where everybody's spread out over the line. And the next one after that is where we might get population spread out according to some negative exponential curve. And a good deal of this is beginning to relate these ideas back to scaling, although we've used an exponential here rather than a power law, basically. Then we said that the probability of, let's say, population at different points in the city with respect to the center is equal to a negative exponential function of the distance, really, from the center, etc. Now, we can derive these models using maximum entropy in this particular context. Now, let me have a look and see how we go. Okay, let me just quickly give you an indication. If we have a population in a probability of a population being in different places in the city, so I equals 1 to n, we have n different places in the city, and therefore the entropy is equal to pi log pi summation over I, giving us the entropy. If we then maximize the entropy, giving people the most choice of where they could probably locate, subject to the fact that the probabilities have to add up to 1, that's the conservation, and also subject to the fact that there has to be a certain amount of travel or distance or cost, basically, for where people locate in that sense. So in that sense, we can derive a formula for pi, in that sense, the probability of location. And the formula that we derive by maximizing that entropy subject to those constraints, and we can use standard procedure, Lagrangian multipliers or whatever to do that sort of basic sort of calculus stuff. And basically we then generate the model, basically, which we show as the negative exponential density function. Now, that's a very widely used model to model things such as rent and wages and travel costs and so on, travel movements and so on, in a city with respect to places which are very central versus with lower costs, basically, to places where there are bigger costs in that particular context. And there are lots of models in our world that really relate to that. If I change it to the log C in that sense, rather than the cost of travel, change it to log, basically, in that sense, then we actually get a power law, basically, in that sense. And we could say that the population in a particular area of the city was equal to the cost of location raised to a power, etc., c to the, minus lambda in that sense, 1 over c to the lambda in this sense. Now, this is not a rank-sized relationship. It's because basically we're not looking at frequencies of populations here. We're looking at the costs of population in that particular context. There's a paper there in geographical analysis by myself about 10 years ago, which really deals with that. Okay. Now, there's a bunch of slides here that I don't really have time to look at, which really relate to things. But what I will do, I'll send the PDF through to Luca, who can then distribute it to you in that sense. And I'm hopeful that this will just give you an indication of where to look with some of these things. Okay, so let me think. Okay, so this is using an entropy maximizing approach to look at the rank size rule, the power law, changes it in that sense. And indeed, there's a paper by myself and a variety of people, two Italian colleagues, Matteo Cristelli and Luciano Pietranero, who's the granddaddy, I should say, of physics in Sapienza. Okay, we wrote that about 10 years. Was it 10 years ago? Yeah, not far, 10 years, my goodness. And so we're looking at different aspects of power laws in that context, and you can look at that. We've not looked at many applications here today. We've looked really at the logic of these things. But if you look in that paper, you'll find some work on that, and then it gives you an indication of that. Okay, now there is another entropy formula which I want to introduce before we finish. And we're on time, certainly. I've been going for an hour. So there's another measure of information, which is what's called an information difference, basically. It's where we have a situation where the probabilities of location are, we might have a prior set of probabilities, and then we observe a posterior set of probabilities. So we might think of this as looking at a system where the population is distributed, say, in the year 2010, and we might then look at the same system with the population distributed in the year 2020. And we want to look at the difference in terms of the difference information between them. So we might say that QI is the population in 2010 and PI is the population in 2020. That's one way of thinking of it. And we might divide our city into, let's say, 100 zones or something like that, where we have 100 values of QI and 100 values of PI. We can form an entropy for each of these. As you can see, I've formed an entropy with respect to QI and PI, but use the expected value of PI in this particular context. And if we form those two entropies and we compare them, basically, we take one entropy, the second entropy really, from the first entropy, in that sense, then what we actually get is the sigma pi log pi over qi. Now, this is called an information difference in that sense. It's a difference really between two entropies, but it has that slight twist in the tail related to the fact that the prior and the posterior entropies are slightly different. We're using the posterior probability distribution to weight the prior, and we're also using it to weight the posterior in that sense. So there is that difference. Now, this is referred to as the Kullback-Leibler information difference formula. It goes back many years, it's back to the 1950s, I think, maybe 1960. And we can also maximize this information or maximize the difference, which to some extent is the minimizing the information. And we can set the problem up in this particular way, that we want to minimize the difference between the prior and the posterior. What actually happens is that you see we have the entropy maximizing equation in the middle of the screen there. And at the bottom of the screen, we have the derivation where we say that the population in I is equal, the posterior population is equal to a negative exponentially weighted version of the prior distribution. Now that makes a lot of sense. If we've got posterior, but we've also got information about prior, then we would, and also information about the constraints, the travel costs and so on, then we'd expect basically to be able to derive a formula as we do there, where PI is equal to QIE to the minus lambda Cij, normalized by the total in that sense. Okay, and that's really the information difference. Now, there's quite a lot of stuff we could say about that. I'm not going to say any more, but we can begin to think of the prior as being an element of space, or the posterior being so on. There are lots of ways of combining different variables in this particular way. So I'm going to stop at that point and then just say something finally about what you can look at. So I'll refer you to another paper in Geographical Systems, and really that's a sort of a paper that that really summarizes some of these ideas that I've just talked about in this particular context. So let me conclude by just saying a few words about complexity and pointing you in directions to other things you can look at. One of the kind of key things is that any measure of complexity has obviously got to deal with size and scale, in a sense, because to some extent, a more complex system is one where the scale changes, the size changes, and also the scale changes. The other feature, of course, that is that complexity, that size and scale intrinsically depend on interactions. You've seen that even in our entropy formulas, we've talked about how one event interacts with another event, basically. One location interacts with another location. So to some extent, complexity is intimately bound up with size and scale. Now, there is no single measure of what is a complex system, basically. It'd be very nice if the world was such that this would be the case, but the world is too complex, really, in and of itself. We're talking about complexity theory. The world is too complex to have a unique definition of complexity theory in that sense. Complexity really defies definition in this particular context. One of the kind of key issues that we've not talked about very much here, but is important, is that entropy and complexity, of course, is a measure of spread or variation. It's to do with how things spread out in space, or whatever the container, system container is that we're talking about in that sense. And all of this hooks into ideas about diversity, variance, spread, and these lead to many other definitions of entropy too. So to some extent, entropy is all about diversity, and complexity is really all about diversity. And there's a lot of work in the literature dealing with these ideas, both qualitative and quantitative. Okay, so if you want to look at some of this sort of stuff that we do in this area, the Urban Informatics book, which you can download from Springer because it's open source, and I think Luca maybe gave you a reading from that. I've written a paper in that called Defining Urban Science. I think it's a short paper, deals a little bit with scaling and so on. Have a look at that. You can download the entire book free, and it deals with smart cities, but a fairly technical book, basically. And my own two books, Cities Complexity and The New Science of Cities, are published by MIT Press a few years ago. Unfortunately, I don't have them online in any sense. You can't log on and get them online, apart from the fact that they've been translated to Chinese. So if you can read Chinese, you can get them online. Basically, somebody's digitized them and so on, that they are available as an open source PDF somewhere, basically. Anyway, I leave you with that, and hopefully this has given you some orientation towards one aspect of urban science. Now, I think it's very important to say that we're only talking about one aspect of urban science here. There are lots and lots of other things that fit together in terms of the material that I'm sure you're going to be talking about in this course. Now, at that point, I want to stop sharing my screen and hand back to Luca